This is Lab 1, Constant Velocity Motion. The purpose of this lab is to pick an object moving in one direction at a constant speed, i.e. constant velocity, and take the data from that and compare it to a VPython model of that same data and see if there's any discrepancy between those two. And if there is, try to explain it. So, I chose for my object a water bottle rolling across the floor. And when I compared it to my VPython model of that same water bottle, turned out the water bottle was moving faster. More than likely, it was because the water bottle was moving towards the phone, and thus appeared to be moving faster than it actually was. So, from a physics standpoint, you have to start from a fundamental principle, i.e. in this case, Newton's second law, or F equals ma. Now, in reality, we want to predict the future velocity of our object given the net force, so we have to use this formula. The velocity in the future is the current velocity plus the net forces on the water bottle over its mass times the change in time. So in this case, we have no net forces on the water bottle, so our velocity is constant, Vf equals Vi for the entire time. So we take a look at the water bottle moving across the screen in Tracker, and we see that we have a nice constant velocity, especially shown by our completely diagonal line, i.e. a constant ratio of change in distance to change in time, which indicates constant velocity. And we can compare that to our VPython model of the same data. Once again, we have moving in constant velocity at a constant time. So that VPython model we can see was constructed from this system. We give it our initial mass and its initial position, velocity, and time based on the tracker data, and the time step of 0.001 seconds, which gives us accurate data throughout very small time steps, making comparison of data much easier. So, while we have a time less than our final time in Tracker, we have our net force at 0 because it constant velocity, and then we use Newton's second law to calculate the new velocity, and the formula Rf equals Ri plus V average delta t to calculate the new position of the ball, which is in this case the model of the water bottle, and then we advance the clock to move to the next iteration of the loop. So, when we compare the two models, the actual observational and the model we predicted with VPython, we see that the observed falls above the predicted model. And once again, this is more than likely because the water bottle is in fact moving towards the camera, which is in this case both the plus x and plus c direction. But all we can see in the tracker video is that it's moving faster, because we interpret the movement in the plus c direction as movement in the plus x direction in this case, because we're projecting it onto 2 dimensions. Thus, we get an underprediction with the VPython, which assumes it's moving parallel to the camera, unlike in reality. So, there are 2 questions we must answer before this lab is concluded. Those are, what if we switch the axes in the tracker video? Say, if we make right is minus x and left being plus x, and can we really determine all the forces that give us a net force of 0 on the water bottle? So, as far as the switching of axes, if we were to switch the axes, then the only thing that would actually change was the sign on the data we got, as in everything that is currently positive would be negative. So, but in reality that would change none of the data, and it would not change any of the results that we got from it, it just make it in another direction. And as far as determining all the forces on the water bottle that give us 0 net force, we have gravity and the floor pushing down, or pulling down and pushing up respectively on the water bottle, giving us 0 vertical net force, and the only horizontal force acting on it is friction, but that's negligible over this distance, or else we'd be slowing down, which would give us a curve, which is what we cannot see in the experimental data. So, in conclusion, the Python model was a good model for this water bottle moving. However, if it had moved parallel to the camera the entire time, it would have been even better.